Thank you very much for the introduction, and also thank you very much to all the organizers for the invitation to speak. So I'm going to talk about joint work with Yves de Cornulier about the behavior of certain class of groups under quasi-isometries. So we start the talk with giving you a theorem due to Kevin White about Bohm-like solitary groups. So before, let me recall the definition. So whenever we're given two integers, m and n, we have the associated Bohm-like solitary group. It's a group given by the following presentation. So it has two generators, t and x, and one relation saying that t conjugates the m power of x to the n power of x. So equivalently, this is the Hennenfent extension of the group Z over the subgroup mz and nz, such that the isomorphism between the two is the multiplication by n mod m. So this class of groups will split into two distinct cases. The case where the first parameter is equal to 1, in that case the group is solvable. In terms of the action and extensions, that means the action and extension is ascending, and in terms of the action on the Basser tree, that means that we have a fixed point in the boundary of the tree. And so we are interested and motivated by the following theorem due to Kevin White, 2001, saying that when the first parameter is at least 2, so for every m and n at least 2, and for every other choice m prime and n prime, so the associated groups, they are all quasi-isometric to each other. So BSMN and BS m prime n prime are quasi-isometric. That would be QA. This is very important to stick to that case. In the case where the first parameter is equal to 1, there's a result of Farb and Mosher saying that the situation is totally opposite. For BS1n, that group is very, very rigid with respect to quasi-isometries. Any group quasi-isometric to it is actually commensurable up to finite kernel to it. So from that perspective, these two subfamilies, they have very, very distinct behavior. So let me say a few words about the general setting we're in. What does it mean quasi-isometric? So whenever we have gamma a finitely generated group, and S finite generating subsets, so we have the associated word length on gamma, which is so just the minimal number of generators that we need to write our element small gamma. And we have the associated left invariant word metric defined by saying that the distance between gamma 1 and gamma 2 is the length of the difference. So this is a proper left invariant word metric on gamma. It depends on the choice of S, but up to quasi-isometry, this does not depend on S, and so gamma has a well-defined quasi-isometry type. Okay, and so in general, isometric actions on metric spaces are an important source of quasi-isometries between groups. So let me recall this. So whenever XD is a proper metric space, so by proper I mean that balls are relatively compact, and we're given an isometric action of a group gamma on X, and so we say that it is proper if whatever K is compact in X, so the set of elements of gamma that do not displace K too much is something finite. And we say it's co-compact if one can find a compact subset F inside S, such that so the gamma translates of X, of F, they cover X. And when it's both proper and co-compact, I will say that it's a geometric action. Okay, and so the reason why that's a source of quasi-isometries between groups is the Milnor-Schwarz lemma. Saying that, so if we have gamma and lambda. Yeah, but do you think it works?
Yes.
Thanks. So the Milnor-Schwarz lemma is saying that if gamma and lambda are two finitely geometric groups, that admit a geometric action on the same space, then gamma and lambda, they are quasi-isometric. So that general fact is the source of most classical examples of quasi-isometries between groups. And so we have the following natural question. So whenever we have gamma and lambda finitely generated groups that we know are quasi-isometric, one can wonder whether they are quasi-isometric because of the Milnor-Schwarz lemma. So are they QI? Because okay, and so I'm going to answer that question for that kind of groups in the end of the talk. So the appropriate setting, the appropriate notion to make that question precise is the notion of commability between groups. And in order to motivate the setting in which I'm going to define that notion, let me rephrase this setting differently. So whenever we have XD like this, a proper metric space, we can consider the group of isometries of XD with the compact open topology. It gives us a locally compact group, G, and saying that a discrete group gamma admits a geometric action on X is the same as saying that modulo some finite normal subgroup, gamma embeds as a discrete and co-compact subgroup inside G, the group of isometries of X. So equivalently, the Milnor-Schwarz lemma can be stated by saying that if gamma and lambda, they both embed up to finite normal subgroup as discrete and co-compact subgroup in the same locally compact group G, then they are quasi-isometric. So from that perspective, we see immediately that locally compact groups come into play, and it turns out that this is the proper setting to define the notion of commability. So,
what restrictions do you have on X? Because if you just take the space of quasi-isometries from gamma to lambda, this is always going to be a metric space, well, with fixed C and fixed constant.
I think that what answers your question is that I'm only considering isometric actions.
Oh, so you don't have an metric on the space.
Right, so you had the topological coupling point of view in mind? Okay, I see. I only consider isometric actions on metric spaces. And I want, yeah, this is the point. So for GH, locally compact, and compactly generated groups, so I will use the following notation. I will use that notation G is parallel to H if G and H have geometric action on the same space. So again, by geometric action, I have to adapt the definition that I get here. So proper now requires that this is relatively compact, and co-compact does not require anything. I'm only considering, say, continuous action, because G now has a topology. And I will, so the terminology is due to Yves Cornulier from 2013, I think. We say that GH are commable if, so we want two groups to have a geometric action on the same space to be commable, and we take the equivalence relation generated by this. So GH are commable if they are related under the equivalence relation generated by that notation. It can be checked that it is indeed not transitive, the property of having a geometric action on the same space. So to get an equivalence relation, we take the transitive closure of that relation.
Is there a reason to restrict the compactly generated for this definition?
No. No, definitely not.
What was the question?
Whether compactly generated is necessary in that definition. It's not, but in that talk I'm only going to consider compactly generated groups. So
But you get the same notion restrict.
you get the same notion. What do you mean?
When you take the transitive closure amongst compactly generated groups versus.
So the property of being compactly generated will be preserved. That answers the question. Okay. Okay, and even if we only are interested in discrete groups, that would be. I mean, I started with some interest in the discrete groups. It's more natural to define this like this and study the commability class of a group, and then eventually looking at discrete groups within that commability class. Okay, and so I should give you the following remark, is that, so there's another notion of equivalence between discrete groups, which is the notion of being commensurable modulo finite kernel. So by this I mean that two groups gamma and lambda are commensurable modulo finite number of subgroups if they have finite index subgroups which admit finite normal subgroups, such that if we mod out, then the groups become isomorphic. So this implies commable, and this implies QI. So this is the Milnor-Schwarz lemma. But in general, commability is much closer to the QI relation than the commensurability relation.
But the thing on the left is an equivalence relation.
It is an equivalence relation, yeah, actually. And that's exactly the point. If you do the same with locally compact groups, it's not...
So it doesn't have a name, it's the left hand of the property.
Some people...
Quasi-isomorphic or something.
Okay.
Something like that. But QI also.
It's also QI. Okay, and maybe at this point I should mention that in general, if we have a discrete finitely generated group gamma, saying something, I mean describing the commability class of gamma is not something easy. For example, it implies, so whenever gamma embeds as a discrete and co-compact subgroup in some locally compact group G, then gamma and G will be commable. So saying something about the commability class of a discrete group gamma is something that is a priori stronger than saying something on all the locally compact groups that contain gamma as a discrete and co-compact subgroup. That was just a side comment, and now, so it's natural to wonder what about the converse of this. So that problem has been suggested by Yves Cornulier in 2013, and it's been answered by Mathieu Carrette and Romain Tessera, so who gave examples of finitely generated groups that are QI but not commable. And so they show the following. So they show that if G is a simple Lie group, and if gamma and lambda inside G are two discrete and co-compact subgroups that have the property that gamma and lambda are not related by this, so not abstractly commensurable or quasi-isomorphic. So two compact lattices that are not that are very different, and then so these groups are obviously commable because they are both co-compact lattices in G. But the thing is that what Tessera and Carrette show is that if we take a free product with Z for the two groups, then they remain quasi-isometric, but they are no longer commable. So that shows that this does not hold. And so let me mention that this relies essentially on the rigidity results of our lattices in simple Lie groups like this. And the strategy of Carrette and Tessera to use these results is relies very much on the fact that these groups, they have infinitely many ends. And so in general, there's no general machine that can say whether two groups are not commable. The only general thing that we know is to check that the groups are not quasi-isometric. So to find groups that are quasi-isometric but not commable, we really need to put our hand on something and have a strategy. And what is really crucial here is the fact that these groups have infinitely many ends. And so in the talk, I'm going to give you different kind of examples of groups that are quasi-isometric but not commable, and they have one end. They are very, very different kind of groups. So in order to do that, I'm actually going to work with a family of groups that is larger than the family of Bohm-Slack solitary groups. So we'll consider the following setting. So given C, a class of groups, so I'm introducing some notation, we denote by T of C, the class of groups gamma, such that gamma admits an action on a locally finite tree, T, so with the following properties. So first, we ask that the action on vertices of the tree has only finitely many orbits. So so the connection with C is the requirement that every vertex stabilizer in gamma belongs to the class C. So for every vertex V inside the tree, gamma V belongs to the class C. So this is a class of groups. So an equivalent way to put it would be to say that if we restrict to action without inversion on the tree, that we consider a graph of groups with vertex stabilizers and edge stabilizers inside the class C, and such that the inclusion of every vertex stabilizer, of every edge stabilizer, in a vertex stabilizer has finite index, so that the associated Basser tree is a locally finite tree. And the group gamma will be the fundamental group of that graph of groups. That's the same thing. And for the purpose of that talk, I'm going to add a third condition on the tree T. So I will exclude some kind of degenerate situations where the tree is bounded or the tree is aligned. I don't want to consider them. So T is not bounded and not quasi-isometric to a line. Finite. Yeah. It will be Z, yeah, because I'm the fact that the action has only finitely many orbits of vertices will imply that.
At least 3 ends.
Mm-hmm.
At least 3 ends.
Exactly, yes. No, better way to phrase it. Okay, and more specifically, we will consider the following class. So we will, notation for this. So whenever D is some integer, at least 1, we'll denote by CD the class of groups that are virtually isomorphic to ZD. And we will denote by T of D the class T of CD. So groups acting on locally finite trees with finitely many orbits of vertices. The tree is not bounded, not aligned, and all vertex stabilizers, they are virtually isomorphic to ZD. So examples. So in the case D equals 1, we have the Bohm-Schlag-Solitar groups. So more generally, people call generalized Bohm-Schlag-Solitar group any group in the class TD such that vertex stabilizers are exactly Z, not virtually Z. And second example, for arbitrary D, we can like generalize the Bohm-Schlag-Solitar construction by taking some channel extension. So we take a matrix M inside G, LD of Q, and I'm assuming that the matrix is not inside G, LD of Z. And I consider the group that I will denote gamma M, which is obtained by taking the HNN extension of the group Z to the D, associated to the following two subgroups. So the fact that M has rational coefficient implies that the matrix M is going to commensurate the subgroup ZD, meaning that the M-1 ZD intersected with ZD will be a finite index subgroup of ZD, and M induces an isomorphism between this and this one. So the associated Basser tree is indeed locally finite, and it will not be bounded nor QI to line by the fact that I'm assuming that my matrix does not preserve globally Z. So just a simple example. We can consider more complicated graphs of groups, and we get more groups.
So the conclusion is gamma ending in CPTD, right?
Thank you. Okay, and so my point towards the end of the talk is to give you a rigidity statement with respect to commability for that class of groups. And in order to state it, I have to introduce something related to these groups, which is a linear representation associated to them. And it's defined in the following way. So first, let me recall the following definition. So whenever we have lambda, a group, we have the group of commensurators of lambda, which is sort of a group of isomorphisms between two finite index subgroups of lambda. So this is an isomorphism. And we model out by the equivalence relation saying that two isomorphisms are the same if they coincide on some finite index subgroup of lambda. That can be checked that it is indeed a group. And the only example that I will need essentially in the talk is the case where if lambda is Z to the D, then the commensurator is a group that we understand. It's just the group GLD of Q. And actually, this is more generally true if lambda is virtually ZD. Okay, and why is it relevant for this kind of groups? That's because of the following reasons. So, if we're given a group gamma inside this class T of D, and we take a tree, as in the definition, and we take a vertex, I fix some vertex in the tree T. So the fact that the tree is locally finite implies that if I consider two stabilizers in gamma of two distinct vertices, then this subgroup are commensurable. Okay? And so in particular, if I'm taking a gamma inside my group gamma, and I consider so the group gamma minus 1, so the conjugate of the stabilizer V inside gamma by gamma minus 1, and I intersect it with the stabilizer of V inside gamma. So this is a subgroup of gamma V, and this is a finite index subgroup of gamma V. And the same thing if I reverse gamma with gamma minus 1. So these are finite. So what does that mean? It means that when gamma acts by conjugation, it sends that subgroup onto that subgroup, and these are two finite index subgroups of this one. So that means that gamma induces an isomorphism between two finite subgroups of gamma V, which produces a group homomorphism from gamma to the group of commensurators to gamma V. And that one, we know that gamma V is virtually Z to the D, and so that group is isomorphic by the above examples to GLD of Q. And we have the following position or definition saying that under the assumption that I put here, that does not depend on any choice. So it does not depend on the choice of the tree T, and it does not depend on the choice of V. And so we denote it rho gamma, so it's a group homomorphism to gamma to GLD of Q. So it's been defined by White, I believe, and White calls it the holonomy representation associated to gamma. So it's really a canonical object that does not depend on any tree associated to gamma.
Kind of equivalence class, I mean, the equivalence class of representation.
Yes, indeed, sorry. So what I did here to define an isomorphism between GLDQ and the vertex stabilizer is the choice of an isomorphism between gamma V and a choice of a basis somehow inside that group. And this is indeed not well defined like this. It's well defined up to conjugation inside GLDQ. Yes, thank you. And maybe one remark, because I started with the case D equals 1, and I will go back to that case eventually. In the case D equals 1, this disappears, that thing, because GL1Q is abelian, so that conjugation thing does not appear. Okay, so examples. Let me go back to my previous examples. So in the case where gamma is the Bohm-Slack-Solitar group, VSMN, so now rho gamma goes to, as I said, GL1Q. And so what is it? So I had two generators T and X, so I need to define only rho on these. So rho of X does not do anything because X belongs to the vertex stabilizer, which is abelian, so it does not act by commensuration on it. So rho of X is equal to 1. And rho of T is precisely the commensuration that we see in the presentation over there. So it's the multiplication by n mod m. So in that setting, people sometimes call it the modular character associated to a generalized Bohm-Slack-Solitar group. And in my second examples, when gamma is equal to gamma m, so again, my representation associated to the stable letter of the Hennenfent extension is just given by the matrix M. And rho gamma is trivial on the vertex stabilizer. And rho gamma equals 1 on ZD. Okay, so how much time do I have?
20 minutes.
30 minutes, thank you. So my goal is to is to say something about the commability class of group gamma inside T of D in terms of the representation that is there. But at this point, I want to have a step back and go back to a comment that I made at the beginning of the talk. So I said that I want to say something or describe the commability class of a group gamma like this, and in particular, it will imply to say something about all locally compact groups that contain gamma as a discrete and co-compact subgroup. And so the proper way to say something like this is actually to define a class of groups that will contain gamma, and we will prove that it is stable under commability. And in order to do this, I cannot stick to discrete groups as I did so far, because I didn't give you examples, but there are definitely examples of groups, locally compact groups that contain, for example, a Bohm-like solitary group as a discrete and co-compact subgroups. And these may not be discrete. So what I have to do in order to state a commability rigidity result in that setting is to actually define a class of groups within locally compact groups that will contain all the examples I'm talking about from the very beginning. So I want to have a step back and give you an additional definition that generalizes the one we've done before. So I will, where is the definition? The definition that I just erased of the class T of D, I want to define a locally compact analog of this. And so the first thing that I have to consider is what would be the locally compact analog of being a virtually ZD. So this is that definition. So we will consider ED the class of locally compact groups O such that so what's the natural way to do? We want something that looks like very much ZD, but is locally compact. So we want to include ZD. We want to include R to the D. So we will also want to include Z to the P times R to the Q when the sum is D. So abelian groups of dimension D. But the thing is that if we are in a setting in which we do not really care about we only care about the large-scale geometry of that group. In the locally compact setting, if there's a compact normal subgroup, this is also some flexibility that we want to include. So I'm trying to motivate that definition. I'm going to consider the groups O such that O has possibly non-trivial. O has a maximal compact normal subgroup K, such that, so the quotient of O mod K is virtually abelian. Is virtually Z to the P times R to the Q with P plus Q equals D. So let me phrase it differently. Abelian groups of dimension D, locally compact abelian groups of dimension D, possibly with an extension by a compact normal subgroup.
Is this the same thing? Is compactly generated and quasi-isometric after the D?
It's not the same, and doing what you suggest would be more natural, but it doesn't work. I really want to put some abelian thing here. So one kind of groups that should appear, but that I don't want to appear, would be the group of isometries of RD. So it would be RD extended by the OD. And that compact group OD acting on RD, I don't want to include this. So starting from D equals 2, it's not the same as the one that you mentioned. And so I'm going to say, maybe I add a comment later in the talk about this, and it's kind of important to restrict to that kind of thing. Because of recent examples of Liri and Minassian. Maybe I will have time to comment, maybe not. Okay, and that was the definition, and so we will consider the class T of ED So what do I mean by this? So same definition as before, but now the groups are locally compact, and I require that the action on the tree is continuous, and same definition as before. So vertex stabilizer in the class ED, and only finitely many bits of vertices, and the tree not 0 or 200. Okay, so in the discrete case, I gave you that definition for the representation of a group gamma inside GLDQ. So exactly the same can be done here. So now the vertex stabilizers, they are more complicated. So the commensurator of a group O like this can be huge because of this compact normal subgroup that can appear. But nevertheless, there's a way. So I mean, the commensurator of O has somehow canonical homomorphism to the commensurator of that abelian group that is over there. And the commensurator of that abelian group over there, it's essentially, it is GLD of R. And so exactly the same way as we did here, there's a way to define the representation. So I'm not giving you details, but so every group G inside that class of group T of ED admits, similarly as before, a representation that I denote rho G, which now takes values inside G or GLDR. And so I'm going to state the theorem in terms of that representation. And in order to state the theorem, so again, as Bashir mentioned before, it's well defined up to conjugation only. And so I need the following definition. So we'll give you a statement saying that a subclass of this, with some condition on the image of the representation, is stable under commability. And my claim is that it's indeed necessary, and it's very related to the comment of Laurent, it's indeed necessary to add some condition on the representation in order to obtain the conclusion that we want. And so the conditions that we have are a bit technical to state. So for the purpose of that talk, I'm going to state something which implies them and which is easier to say. So given a matrix inside GLDR, so there's probably a good name for this, but I don't know it, so I will call it nice. If the spectrum of M has the following property, so M has D, distinct eigenvalues, and they all have a distinct module. And I also want the module to be different from 1. Okay, that's just the definition. And one last definition. So whenever I'm given two subgroups S and T inside GLDR, I will say that they are conjugate commensurate if there's an element G inside GLDR such that G, S, G minus 1 and T are commensurate. Okay, and the theorem is the following. So whenever we fix some integer D, and we consider the class of locally compact groups G inside T of ED, such that the image of the representation of rho G contains a nice element that's a long sentence, is stable under Commability. And not only this, if two subgroups in that class are commable, then essentially they must have the same image for that representation. But since this image is only well defined up to conjugation, the conclusion is that the images are conjugate commensurate. Then rho G of G and rho H of H Let's go back to discrete groups. What does it say? It says that, for example, if we take a group gamma M, as we had before, if the matrix M satisfies the nice condition, then the group gamma, the theorem implies in particular the following. Whenever G is a locally compact group containing gamma as a discrete and co-compact subgroup, then actually G also acts on a tree. So now, G belongs to the class CD. Okay, and if we go back to the motivating examples from the very beginning, so the Baum-Slack solitary groups, we've said that the image of the representation is the subgroup generated by M mod n, and I've put from the very beginning the assumption that M mod n is different from 1, meaning that this nice condition when D equals 1 only means that the rational number is not plus or minus 1. So this is always satisfied in the BSMN case, so nothing to check. And so then what would be the conclusion would be that if I'm taking two Baum-Slack solitary groups that are commable, the theorem will tell me that the images of their representation, they are conjugate commensurate. But conjugate commensurate in dimension 1, since the group is abelian, only means commensurate. So that means that when you specify to that theorem to the case of Baum-Slack solitary groups, it says that if two BSMN and BSM'(n') are commable, then we have some strong conclusion on M mod n and M' mod n', which is the following. So let me state it as a corollary. So if BS Mn and BS M'(n') are commable, so let me phrase it differently. I will say if n mod m and n prime mod n prime do not have a common power. So it just means that the cyclic subgroup of Q star that they generate are not commensurable. If these do not have a common power, then the groups BS Mn and BS M'(n') are not commable. So it gives us an infinite family of groups which are all quasi-isometric thanks to the result of White, and they're not commable. The converse, we don't know. So the question is whether between Baum-Slack solitary groups that condition characterizes commability. We don't know. Okay. I have 3 minutes, or what? I didn't.
You have 5 minutes.
I have 5 minutes, thank you. So, what I can do now is is maybe do something that I should have done before. About that class of groups, this one, the discrete ones, meaning T, the class TD. So it's been studied a lot, and I didn't say it, but it's been studied a lot with respect to the behavior with respect to quasi-isometries. So this we know very well. So there's the first result of Mosher, Sagev, and White saying that that class of group is stable under quasi-isometries. So any group quasi-isometric to a group in TD actually belongs to TD. And then within that class of groups, saying that two groups in there are quasi-isometric to each other, it also splits into two distinct cases. There's the solvable case, in which the work of Farb and Mosher, saying that the situation is very rigid, groups tend to not to be quasi-isometric to each other, and there's a non-solvable case. And in the non-solvable case, there's a theorem of White that generalizes the theorem that is there for D equals 1, that essentially that says something about the commensurability class of a groups like this in terms of this representation. This is why White cares about that representation. So White showed that if two groups in TD are quasi-isometric, then the images of their representation, they are at bounded Hausdorff distance from each other. So this goes in the rigidity side. And White also shows that within, if we fix a class, a Hausdorff class, with the property of being at a Hausdorff distance from each other, then apart the generic cases, all groups like this are quasi-isometric. So this is the analog of the result that is there. So the reason why I'm mentioning this is that this is that theorem really should be compared to that, because White is saying that the quasi-isometric class of a group like this detects the image up to the property of being at bounded distance from each other, so something very coarse. While that theorem says that the commability class of a groups like this, so something stronger, it detects a finer invariant, because it's not the property of being of bounded Hausdorff distance from each other, it's the property of being commensurable up to that conjugation error. So in particular, I gave you examples in dimension 1, but in any dimension, combining that result and the result of White, we obtain groups that are quasi-isometric but not commable. That was one comment, and maybe the last comment is would be about that condition. So I claim that it's necessary to add some condition on the representation in order to obtain the conclusion that the images of the representation are conjugate. And the reason comes from recent examples of groups studied by Leary and Minassian, who studied the groups gamma that I denoted gamma M in the case where the matrix M is orthogonal. For example, SODQ. So starting from D at least 2, the group SODQ, it's an infinite group. And so these groups, gamma M, they admit an affine action on R, which in the case where the matrix M is orthogonal, that action becomes isometric. So they admit an isometric action on RD. And that action is definitely not proper, but this group also acts on a tree. That action is definitely not proper either, but if we consider kind of a product action of these two, we obtain a geometric action on RD times the tree. And Leary and Minassian show that this action is geometric, so it's proper and co-compact. So in particular, the groups gamma M for M orthogonal, they act geometrically in RD times the tree, but there are also stupid groups acting isometrically on RD times the tree. For example, Z to the D times a free group. And so these example gamma M for M orthogonal, they are always commable to ZD times a free group. But for ZD times a free group, the White representation rho gamma is definitely trivial because the ZD is central, so there's no commensuration in there, it's only centralized. While for the groups gamma M, the image of the representation is the infinite cyclic subgroup generated by M. So these examples show that the theorem is definitely false for this example. So this is why the nice element condition is there. And it also explains a little bit the question of Laurent, because I didn't want to include groups of isometries over there on RD. And this is in the case of in the Commability, for the examples of Liri and Minassian, these groups definitely appear, and this is why they act geometrically on RD times the tree. I'll stop here. Thank you.
Questions? Comments?
I have a main question. Where does combability come from? The word.
The name?
Yeah.
So Yves is there, so I'll let to you.
Why do you choose this name? I found that. This question I asked myself.
So as not to call it like stormy weekly, almost uninsurable or things like this. So that you can remember it.
It's just a short form of unmeasurable.
It's not uninsurable.
I have a question. I mean, is there a measurable analog statement to this white result? I mean, measure equivalent. Are there measure equivalent? This is lots of subgroups.
Can you repeat the question?
Is there
Yes.
a measure equivalence? I mean, analog of this question, all this question. And, I mean, commability,
So there's definitely a question, and the answer is not known. It's not known how these behave with respect to measure equivalence. And maybe I can add a comment. All we do here, I stated this for example, two discrete groups being co-compact lattices in the same locally compact group. This implies commable. But what we do in the proof actually applies to also say something about, so given a group gamma inside TD, on the locally compact group into which gamma embeds as a lattice, not necessarily co-compact. So in particular, in the case of the groups BSMN, under that same condition over there, we know that they do not embed as lattices in the same locally compact group.
So they're not measurably probable.
Not measurably.
But we don't know whether they are measurably equivalent.
I don't know. It's been studied. I should have said it. There's a paper by Kida saying something about orbit equivalence between these kind of groups, and under a strong assumption on the kind of actions that are under consideration, and also something of Udaye and Ram, but same flavor, under some assumptions on the actions.
Is there another question you want to ask? Maybe when it's lunchtime. Lunchtime is in 5 minutes. Thank you.